Welcome to Learning to the Engineer. In this video, we will focus on the concept of virtual ground and solve some problems based on that. We will also see the characteristics of operational amplifiers to understand how they behave with the different inputs. Let's get started. Mostly, an operational amplifier will be used as a negative feedback when we are trying to amplify the input. But in different applications, we are using positive feedback too. Like a Smith trigger, in multivibrator and all, we use positive feedback. When we are using an operational amplifier as a comparator, we don't need any feedback, just the two inputs will be wired to the positive and the negative terminals of an op-amp. Then we'll get the compared, we'll find the difference of these two in the output. Now we will focus on the negative feedback alone. Consider an operational amplifier circuit like this. You have the input resistance here and we have the feedback resistor connected here. Consider that this resistor is RF and this is Rin. We are applying a very small input Vin via this terminal. This is very small. It will even be like 0.01 to something like 0.1. This will be the range of the input that's generally applied over here. It will be maximum of, let us say, 1 volt. Okay, we cannot go beyond that. Okay, and the positive terminal is directly grounded. This is a real ground because we are grounding this terminal, whereas this terminal is 0 volt and we call this as a virtual ground. This is because the negative terminal will be tracking the input at the positive terminal and hence both these voltages will be at the same level at all times. Be it ideal op-amp or practical op-amp, both these terminals are designed to track each other. Okay, so when we are grounding this terminal, this voltage will be tracked by this and the voltage here is 0 volt, and this is just not enough to understand this concept. This input is very small, and what will be the voltage at this node? It will be a fraction of this, which is even smaller than this range. Okay, so which is close to 0 volt. So we consider that there is a short here, but this is not a real short. This is a virtual short. Okay, and hence this is called as a virtual ground. Okay, so when is this concept applicable? Can we apply this to all operational amplifier circuits? No, we cannot. We can apply that only to ideal operational amplifier. Ideal amplifier meaning the gain is infinity. In a problem, if they give you that the open loop gain is, let us say, 10,000 or 20,000, in those cases the gain is finite, it is not infinite. So which means that this is a practical op-amp and not an ideal op-amp. In another case, they will also give you the model number of the operational amplifier, let us say LM741 or something like that. So we can understand that this is a practical op-amp and ideal op-amp cases are not applicable for this. So these are considered to be close approximation of the ideal case and not the exact one. To simplify the calculations and to make the circuits look easier for us, we are having this virtual ground concept. And there are a few other cases where this is not applicable. First one is practical op-amp, like I said. If we have a practical op-amp, this is not applicable. And second thing is when we have positive feedback. When we have possible feedback, let's say for example Schmidt trigger or multivibrator. So in these cases, we have a positive feedback and hence this concept is not applicable. And also when we are seeing the op-amp as a comparator, the configuration itself is different. Okay, so again this is not applicable because when you are considering a comparator, you will apply two voltages to this. One will be the positive voltage. The inverting terminal voltage will be, let us say for example 10 volt, and this voltage will be, let us say for example 5 volt. Okay, so this operational amplifier compares these two. If this is higher, if the inverting terminal is higher, the V out will be negative. Okay, it will be negative and it will be equal to minus VEE, and it will be equal to plus VCC if the positive terminal has a higher voltage. Okay, so this is a comparator and we do not have a feedback resistor over here. So in that case, we cannot say that this terminal's voltage is tracked by this and so on. That is not applicable. The purpose of this circuit is entirely different. So in these three cases, we cannot use the concept of virtual ground. Okay, now let us go to another part of this video. We will see the characteristics of an operational amplifier. Consider that this op-amp has a gain of 2 into 10 to the power of 4. Okay, and let us say we are applying an input voltage of 0.1 volt. What will be the output? The output will be 0.1 into 2 into 10 to the power of 4. So the output will be 2 into 10 to the power of 3 volt, right? Is it right? We cannot say that. It depends on the characteristics of an op-amp. It doesn't mean that whatever be the input at the voltage input, we will have the same gain and we will get the same output. That is not the case. Okay, we have to check the characteristics of an op-amp. With every device, we will get something called as a data sheet. It will tell us the specifications of that device. So similarly for operational amplifier, we will have characteristics with respect to input and output. Minus V in and this is minus V out. Okay, so as we increase the input, up to a certain point, the output will be increasing linearly. Okay, it's same for the positive as well as for the negative. And after this point, it will be saturated to the same level of output. This will be plus VCC and this will be minus VEE. Okay, so just because we call this as an amplifier, it doesn't mean that if we supply input in few millivolts or volts, exactly it will be amplified and you will get a multiplied value of output. That is not the case. It occurs only to a maximum value of VCC and minimum value of minus VEE. So the operating amplifier will work linearly between these two ranges, between VCC and minus VEE. This is called as the linear region of op-amp, meaning the output will linearly increase up to plus VCC. If this goes beyond plus VCC, if input goes beyond that, then the output will be saturated at one point. Okay, so these levels of voltages you can find it at the data sheet. Okay, so let me give you a question. Okay, you just can pause this video, think for a moment and type the answer. Okay, what will happen if plus VCC is 0 volt? You don't connect any operating voltage to that amplifier, but you are connecting only supply input, the input that you want to amplify. But you are not giving any VCC, you are not giving any operational voltage. What will happen? What will be the output? Will this get amplified or will it be 0? Okay, so type your answer in the comment section, and now let's solve some problems using the virtual ground concept. For the circuit shown in the figure, find out the output voltage. In this figure, we have two inputs that is applied. One is the 3 volt that is applied via the negative terminal, and there is a current source connected to the positive terminal. First, we will use source transformation to find out the equivalent voltage source in series with the resistor. If you are not familiar with the source transformation technique, you can check the video in this link and then come to this video. Okay, so now I'll quickly solve this area alone using source transformation. The voltage input is 1 microampere into 4 mega ohm, which is 4 volt. Okay, so we have a 4 volt in series with 4 mega ohm. we have a 4 mega ohm resistor in series with 4 volt. Okay, so we know one concept, that there is no current that is entering the terminals of an op-amp. Both the inverting and the non-inverting terminals doesn't accept any current. Okay, so when there is zero current, then there is no meaning of having this resistor actually. So this 4 volt is directly applied to this terminal only. Okay, so this will be tracked by this negative terminal, and the voltage at this end will also be 4 volt. Okay, so what is the current that is entering this 1 kilo ohm? Let us call this as I1, and the same I1 will go via the feedback resistor and meet the output, and the feedback will be coming here. Okay, so there is no current that is going inside. By Kirchhoff's current law, I1 goes straight into the feedback resistor. Okay, so let's find out I1. 3 minus 4 divided by 1000 is equal to 4 minus V out divided by, this is 17,100. Okay, both of them are in series, so we are adding these resistors. If two resistances are in series, why are we adding the value of the resistance? And if they are in parallel, why are we not adding them? Check out this video and you will understand this concept better. Okay, so since both of them are in series, we are adding these resistances and this is the value. So let's cancel the terms. We will be getting minus 0.1 is equal to 4 minus V out divided by 171. So this implies that I am taking this 171 here. Minus 17.1 is equal to 4 minus V out. So the value of V out will be 4 plus 17.1, which is 21.1 volt. Okay, yeah, so this is the value of the output voltage. Now we will solve another problem to understand the effect of feedback resistor. What will happen if this feedback resistor is in negative terminal? What will happen if this is present in the positive terminal? We will understand that through the next problem. Referring to the circuit shown in the figure, find the terminal which is non-inverting if VA is 0 volt, VB is 1 volt and V out is 8 volt. The first subdivision of this problem is RA equal to RB equal to 10 kilo ohm and R1 is given as 70 kilo ohm and R2 is infinity. So under these conditions, we are supposed to find out which is the non-inverting terminal. It is given that VA is equal to 0 volt. So meaning this is directly connected to the ground. Okay. VB is given as 1 volt. 1 volt. Okay. And V out is equal to 8 volt. This voltage is positive. So where are we applying the input? By this time you would have guessed the answer. Okay, I'm still going to solve this problem for you. Okay, so by this information itself, you can simply guess which terminal, A or B, which is inverting, which is non-inverting. You should have guessed by this time. Okay, so and in the first subdivision, it is given that RA and RB are same, which is equal to 10 kilo ohm. Okay, fine. So what is the value of the feedback? R1 is given as 70 kilo ohm and R2 is infinity. What do you mean by saying that a resistance is infinite? When will you have the resistance to be infinite? When there is an open circuit, meaning there is an open circuit over here. So there is no meaning of having this resistor. There is no feedback path provided via the B terminal. Only the A terminal has a feedback resistor which has 70 kilo ohm. Okay, and okay, so when the output is positive, we can simply understand that this is a non-inverting amplifier. The power is supplied via the positive terminal. Okay, so this is what we can simply understand when we say that the output voltage is positive. Okay, still we will use KVL, solve this problem and then find out the answer. Okay, when this terminal has 1 volt and there is no feedback connected, the current through the amplifier is 0 ohm 0 ampere, I'm sorry, okay, into these terminals there is no current that's going, okay. So we do not have any current flowing into this circuit because this is one single series line and there is 0 ampere. So what is the voltage at this terminal, B terminal? It is 1 volt and hence it will be tracked by the A terminal, and 1 volt is the voltage across the A terminal, right? So we'll apply Kirchhoff's laws. By the Kirchhoff's current law, we can just assume that both these currents are outgoing, okay. So 1 minus 0 divided by 10,000 plus 1 minus V out divided by 70,000 is equal to 8, right? 8 volt is not 8, I'm sorry, this is just KVL, which is 0, okay. So now let's find out the value of output voltage, okay. So if you simplify, it will be 1 is equal to V out minus 1 divided by here you have 10,000, okay. So this will be 7. So 7 plus 1 is equal to V out, which is equal to 8 volt. The answer is right, right? So we can say that this terminal is negative and this is positive, okay. A is negative, B is positive in this case, okay. Just when the output is positive, we can say that power supply is connected to the positive terminal, okay. So since this is 0 volt, only there is power given via the B terminal, so hence this terminal is positive, okay. So now we understand the importance of this feedback resistor. Here we didn't have any feedback, but here we had feedback, okay. So if we didn't have any feedback, there won't be any current coming via the input resistor. There is no meaning in having this resistor if you don't have a feedback, right? If you say, let us say for example, this is 45 ohm, okay, and you don't have any resistor connected in the feedback. So when what is the current? Current is again 0 ampere, because whatever be this current, it goes only via the feedback resistor. It doesn't enter into the op-amp. So you don't have any meaning in having a input resistance when you say that you don't have a feedback resistance. Consider this terminal. You had an input resistance and you had a feedback resistance. Only then this 10 kilo ohm made sense. Even if you had 10, 20, 30, 40, whatever be the value of this resistance, unless you have a feedback connected, this resistance doesn't have any meaning, okay. There is another subdivision to this problem which I wanted you to try, okay. Now if VA is 10 volt and VB is 0 volt, and if B is the inverting input, select the value of RA, RB, R1 and R2 to obtain an output voltage of 20 volt. It is similar to this workout, okay. By just understanding the problem well enough, you can just by reading the question you can answer this question, you can answer this problem, or you just try to work out the value of the resistors, okay. So once you find out the answer, type that down in the comment section. If you have any doubt in this concept or anything in analog electronics, do write to learningtoengineer@gmail.com and I'll be happy to answer your questions. Thank you.